Welcome to Brain Vision.
Hello. Now we will be working on the problem 11.91 of Young's book. Here we have a wire hanging from a support and a fish hanging from the wire at the bottom. My given values are the mass of the wire, the unstretched length of the wire, the cross sectional area of the wire. This is the mass of the fish. This is the unstretched length of the wire, and this one is the cross sectional area of the wire, and g is my acceleration due to gravity. So we have to assume here that the wire is completely massless. Now you can see that the wire is in tension here because of the fish hanging from it. Let's draw the forces acting on the wire and on the fish. I have already drawn them here. So this is the free body diagram of the wire. So we have tension forces acting on the wire because of the fish hanging from it, and this is the free body diagram of the fish. So we have the gravitational force acting downward and the tension force due to the wire acting upward on the fish. Since the whole system is in equilibrium here, we can say that the tension force is equals to mg. Now let's use our equation 11.10 from the Young's book to find the stretch in wire when the fish is hanging from here. We get the equation which says the Young's modulus is equal to tensile stress over tensile strain. The tensile stress is given by the tensile force over cross sectional area, and the tensile strain is given by the change in length over length. So I can use this equation to find my change in length or the stretch in wire, which gives me this equation mgl over ay. So from here onwards I'll use notations where I'll say that delta L as dl, and I'll denote L naught as L. So we have all the unknowns here except for the Young's modulus. So Young's modulus is basically a constant, and for steel, our wire is made of steel. So for steel, the Young's modulus is 20 times 10 to the power 10 newtons per meter square. So plugging all those values in this equation, we get our stretch in wire to be 6.62 times times 10 to the power minus 4 meter. I'll say this dl as dle because this is the this is the stretching in the wire when the wire is at equilibrium. So let's say this dle. Now let's move on to the next part. So in the next part, we have a slowly varying force F, which is applied at the lower end of the wire, and the change in length is given as delta L. So my change in length because of the varying force is given to be 5 times 10 to the power minus 4 meter. So in part B, it asks us what is the work done by the gravitational force. So work done is basically given by integral over F dot dx. Since my gravitational force is a constant, so this equation then gives F dot d, where d is the displacement and here this is the stretch in the wire. I'm sorry. So we have F as mass times gravity and dl as this value. So plugging all these values into this equation, we get my work done as 2.2 times 10 to the power minus 2 joules. So this is the work done due to gravity when we have a varying force applied on the wire at the bottom. So for the third question asks us to find the work done by the varying force that is being applied. So for to start with, I'll again use equation 11.10, which gives me my equation for Young's modulus as a function of stress and strain. So using this equation, can find my force to be Y times A times dl over L. Now since the wire is getting stretched over here, I can assume my wire to be a spring, to be acting like a spring, and by Hooke's law, we can say that the force or the spring force is equal to the spring constant K times the change in length, which is our stretch here. So that gives me K times dl. So now I can use these two equations to find my value of K, which is given by the Young's modulus times the cross sectional area over the unstretched length of the wire. I have all these values and I can just plug those values into this equation and I get my value of spring constant to be this, which is 66666.67 Newton per meters. Now, my work done in a spring is basically half kx square. I have my k, which is given by this equation. I have my x, which is given by dl. And I'll plug these two values into this equation to find my work. And I get this as 8.33 times 10 to the power minus 3 joules. So this is the work done by the spring. This is the work done by the varying force on the wire. Now, for the next part, it asks us to find the work done by the wire. So we know that by Newton's third law that every action has an equal and opposite reaction. So we can say that the force by the wire is equal and opposite to the force acting on the wire. So the total force acting on the wire is equal to the sum of the gravitational force and the varying force that is being applied. Now, let's go back to part C where we found the work done by our varying force to be this equation. There we used the force due to the varying force. So our work done came as an integral which was half kx square. Here, if we say if we take the average value of the varying force, then we can say the varying force is equal to W over dl from this equation. We get this value as, so we basically use the work done by varying force which we calculated from part C, and dl is already given, and we found the average value of the varying force to be 16.7 Newton. Again, we plug this back into this equation. So we get the force by the wire is equal to 60.8 newtons. So now the work done by the wire will equal to the force times displacement, the dot product of force and displacement. But since they are along the same direction, we can say that no, sorry, they are not along the same direction. They have the opposite direction. So our cos theta will be -1, and this will give us our value of work to be 3.04 times 10 to the power -2 joules. But since the force and displacement are along opposite directions, so our cos theta is -1, so there is a negative sign here. So now for the last part, it asks us to change in potential energy. So our potential energy for a spring is given by half kx square. So our change in potential energy du will be half kx2 square minus half kx1 square, where my x1 and x2 are given by, so x1 is basically the stretch in wire when is it is at equilibrium. So it is basically our DLE, which we found from this equation. So this value is 6.62 times, oops, I'm so sorry, 6.62 times 10 to the power minus 4 meter. And this x2 is the total stretch in wire, which means this is the stretch in wire when it is at equilibrium plus the stretch in wire due to the varying force. So we add those two stretches and we get this value to be 11.62 times 10 to the power minus 2 meter. So we plug these two values into this equation and we already have all the variables, all the values of the variables we need. So we plug those in there and we get our change in potential energy to be 3.04 times 10 to the power minus 2 joules. So as you can see, the work done by the wire is negative of the change in potential energy. So from here we can say that the tensile force is conserved. Thank you.